If you've been tracking AI research lately, you've probably noticed a quiet but massive shift happening under the hood. For years, self-attention has been the undisputed backbone of sequence modeling. It works beautifully, but it carries a steep computational price: quadratic scaling. Double your context window, and you're looking at 4 times the flops. That bottleneck has pushed the community to hunt for an architecture that preserves transformer-level performance while scaling linearly with sequence length. The answer that's been gaining serious traction is the state space model, and more specifically, the Mamba architecture. To understand why this matters, we need to step back and look at what a state space model actually does. In control theory, a state space model describes how a dynamic system evolves over time using a set of first-order differential equations. You track a hidden state that gets updated at each time step, and you produce an output based on that state. When we translate this into machine learning, we're essentially learning those transition dynamics directly from data. The original S4 paper demonstrated that you could parameterize these continuous time systems using diagonal plus low-rank matrices, which made training stable and mathematically tractable. But there was a fundamental limitation: those parameters were static. Once trained, the model applied the same filter to every token, regardless of what the input actually contained. Mamba solves that with a single, well-designed mechanism: selective scanning. Instead of applying a fixed convolutional or recurrent filter, Mamba makes the state space parameters a direct function of the input. The model can now decide, token by token, what information to retain and what to discard. Under the hood, you're working with a discretized version of the continuous system, typically using zero-order hold to convert the differential equations into a discrete recurrence. The hidden state update looks like h sub t equals a bar times h sub t minus 1, plus b bar times x sub t, and the output is c times h sub t. The breakthrough is that a bar, b bar, and c are dynamically computed from the current input x sub t using lightweight projection layers. This turns a standard linear recurrence into an input-dependent filter, giving the model adaptive memory without sacrificing structural simplicity. Now, recurrent architectures are notoriously difficult to parallelize during training. You can't compute step t until step t minus 1 is finished, which bottlenecks throughput on modern GPUs. Mamba gets around this with a hardware-aware parallel scan algorithm. Instead of processing the sequence strictly left to right, it chunks the data, computes local state transitions independently, and then combines them using a tree-based reduction. This allows you to train on massive batch sizes and long contexts without blowing up memory or losing precision. During inference, it gracefully falls back to a simple sequential loop, which means you can stream tokens at near-ideal throughput. No growing KV cache, no quadratic attention overhead, just clean linear scaling. The practical impact is already showing up in benchmarks and real-world deployments. On language modeling, Mamba matches or exceeds transformer baselines on long context tasks, while using significantly less activation memory. On sequence-heavy domains like genomics, time series forecasting, and long document reasoning, it's proving exceptionally efficient because it naturally compresses historical information into a compact hidden state. And because the architecture is so lightweight, it's becoming a strong candidate for on-device and edge inference, where compute, latency, and power are strictly constrained. That said, it's not a universal replacement. Transformers still dominate when you need precise, global attention patterns, especially for multi-hop reasoning, complex instruction following, or tasks requiring explicit cross-token alignment. Mamba excels at pattern extraction, sequence compression, and long-range dependency tracking. The most likely path forward isn't a strict either-or, but a hybrid pipeline where state space models handle the heavy lifting of sequence compression and context retention, while attention modules step in for targeted, high-fidelity reasoning. If you want to dig into the math behind the parallel scan, or see how selective scanning compares to traditional positional encoding and rotary embeddings, the original papers and open-source implementations are a goldmine. I'll drop direct links in the description. Let me know in the comments which architectural direction you think will define the next generation of efficient AI, and I'll see you in the next deep dive.